The cash register display. The raw count is an integer, 7 customers, but the manager wants to analyze trend on a scale where regression works. The link function converts the count to that scale. The inverse link converts predictions back to counts. 3 common link functions. Identity, the expected value, is the linear predictor, used in linear regression. Log, the log of the expected value, is the linear predictor, used in Poisson and negative binomial regression. Ensures predictions are positive, you can't have negative counts. Logit, the log odds of the probability, is the linear predictor, used in logistic regression. Ensures predictions are between 0 and 1. The link function is the mathematical bridge between what you observe and what regression can handle. Logistic regression from the Recipe Lab video, reframed. The outcome is binary, 0 or 1. The distribution is Bernoulli. The link function is logit, log of p over 1 minus p. The linear predictor gives log odds. Exponentiate to get the odds ratio. Apply the inverse logit to get the probability. Logistic regression is a GLM. So is linear regression. So is Poisson regression. The GLM framework unifies all three. Once you understand the 3 components: distribution, linear predictor, link, you can build any regression model. DESeq step by step. Step 1. Estimate size factors. Normalize for sequencing depth. Each sample gets a scaling factor based on the median ratio method. Step 2. Estimate dispersions. First, gene-wise, fit a negative binomial to each gene independently. Then shrinkage, pull extreme dispersion estimates toward a smooth trend across genes, the empirical-based shrinkage that stabilizes estimates for low-count genes. Step 3. Fit the GLM, negative binomial with log link. Coefficients represent log fold changes. Step 4. Test significance. Wald's test or likelihood ratio test. Adjust p-values for multiple testing with Benjamini-Hochberg. The volcano plot displays the GLM coefficients on the x-axis and the adjusted p-values on the y-axis. Single-cell RNA-seq adds a complication: zeros. Lots of zeros. A gene might be expressed but not captured, dropout. scVI handles this with a zero-inflated negative binomial model, ZINB. The variational autoencoder learns the negative binomial parameters mean and dispersion, and the dropout probability for each gene in each cell. The ZINB accounts for both biological zeros, the gene truly isn't expressed, and technical zeros, the gene is expressed but the transcript wasn't captured. This is the count model underlying the Census Bureau pipeline. How do you know the GLM is correct? Deviance residuals should look like standard normals. Plot them against predicted values and check for patterns. The overdispersion statistic, residual deviance divided by residual degrees of freedom, should be near 1. Much greater than 1 means overdispersion not captured by the model. Ake and Big compare models. Call back to the photographer. A Poisson GLM with high overdispersion will have worse Ake than a negative binomial. The model check prevents you from publishing false discoveries. Linear regression for bell curves. Poisson for rare event counts. Negative binomial for overdispersed counts. Zero-inflated models for dropout. The GLM framework, distribution plus link plus linear predictor, unifies them all. DESeq is a negative binomial GLM with empirical Bayes dispersion shrinkage. scVI is a ZINB learned by a neural network. Now you know what's inside the black box.